So hello there, can you hear me? Please let me know in the chat. So can you hear and see me well? Plus minus. Ready to start. Today we'll see something really interesting, I hope, regarding the first lecture about deep learning artificial neural networks, classification, regression, and then let me check. I think next time we will start already on something even more fun regarding the language models. I think, let me see. Yeah, so next time we'll look at the language models, so the prompt engineering and generative models, but this time this is the fundamental part of how these models work, to understand what to expect from them, and also to be able to set up some of the models for yourself. So, for example, the prediction of price, prediction of churn, prediction of demand, or if you order such a models from professionals, so that then you understand what are you ordering and what you need in this whole process. So that's the point of today's lecture. And of course, as previously, we're starting working more and more with actual tools where you can play around and test yourself. We'll look also at the homework. I saw that many people submitted the homework, so we'll see the results of that. And remember, the homeworks are part of the mark, and they're not particularly difficult. You just need to understand a little bit what you're doing, and even not that much. So I see pluses in the chat. Thank you for that. So you hear me. If anything happens with the stream, let me know. So today, the idea is that we will look at what is these deep learning models, artificial neural networks, and how to use them. And I set up a couple of ways how you can play around with them. So we'll start from very easy ways and then go to more complex and more actually useful ways. So to understand what it is, so it comes from this biological notion of modeling the natural neural networks into the computer systems, and it comes back to the perceptrons and the Rosenblatt and all sorts of researchers from 50s and 60s last century. So the idea was that I have some kind of neuron which accumulates basically the impulse over time, the electrical charge, and it could be modeled mathematically. If any of you understands a little bit of mathematics, by the way, I just realized I didn't go through the homeworks, so let me give you a little bit of intro into the deep learning models, or maybe we'll go through the whole stuff, and then we can look at homeworks at the end, maybe. No, let's sorry for that. Sorry for interruption. We'll go back here. It will be super confusing if we'll jump back and forth. Just want to share that we did had homeworks, and these homeworks had a lot of submissions, and I want to show you those a little bit. So let me see. So what we had to do, so we had two tasks actually. We really jumped into these deep neural network tasks without showing you those before. So we had, for one, I gave you the data set and I asked you to model dimension reduction algorithms, and I gave you a couple of ways how to do that, either using ChatGPT, using your own coding, using some of the tools I gave you, and the clustering as well. And then the other one is the decision tree, where I also give you the data set. Again, different data set. Oh no, that's the same data set, but so there was the prediction of customer type should be implemented, and another one was color by species. Okay, cool. I think so, right. So, and let me share you some results from students. There are many that submitted these works. So that is really nice that many of you actually take seriously this course. So let me see. And today's work then you will like even more because you will have more things to play around. So one person implemented two-dimensional PCA reduction with probably with Python, because I see that this kind of output comes from Python. So really appreciate that. So this seems PCA and clustered probably by these classes. So then many of you used the BigML web tool, and I did not see anyone using this AI Studio tool. So AI Studio. So I really recommend somebody to install this AI Studio tool. We will work with this today as well. This is something Altair AI Studio that helps to understand what's actually possible with these technologies and models. So I will maybe save it somewhere and share it to you, so later you can find it as well. So this one. And today we also will have web-based alternative as well, but this is like more things you can do with this. Okay, so the clusters, 3 clusters discovered from supermarket data here. So here is also, I think maybe in my task description I had a problem because I saw something about species there, but we have supermarket data. Let me actually check this. Okay, so this is the AI Studio. I don't need that. Let's go back here. Just a second, I will check my homework task description. I don't like it that I have a little bit not open it here. So what did I have there? So clustering. Okay. Implement clustering model for animal dataset. Maybe I didn't give you the right dataset. So I need to look up that. So, but anyways, I saw that many of you try to do clustering, which is good. Okay, wrong dataset maybe. So at least you try to play around with this tool. So again, as you see here in the pictures, PCA1 means that first dimension covered 80% of variation, and then when you go down, then there is less importance to these dimensions. So it seems that it never, okay, so this is not exact same task. You can easily see if this is copied from colleague because the numbers are cannot really be exactly the same. So that's that. Here is somebody implemented even using this this linear separation function. It seems like, so it's really nice, really visually nice. Good job here. Somebody tried to implement it with a. It seems with this is, it looks like ChatGPT. Also nice that somebody tried to do that. Then again with these tools, so this also looks really nice. So and then with the with the decision tree. So customer type here in the top. Sorry. So customer type here in the top. So this is good. Somebody implemented the customer types by these categories. So this is good. This person did not change it to these numeric categories, but the BigML understood that these are categories, so this worked. But I saw that the first person actually did a little bit more job, so this was nice. So here as well, the categories. So basically, what it means is, let's see. So yeah, so if we if we're not from this city. If you're not buying that product line, if you're buying that quantity and so on, then you are a member of that group. So basically, that's what means these decision trees. So this was just like a quick break to look at what I wanted to show you from last time. Now let's go back here. Again, as I say, thank you for, I think it was like over 20 students who submitted the homeworks for both, so that's really nice, and please keep doing it. So then today's session. So again, so we're trying to model these neural networks with these mathematical functions, and what actually happens here is it's easy to understand if you like. It's not that difficult, right? I saw some question here is in the chat. So right, yeah. So the wrong dataset. Yes, please use the dataset that you had there. I will change the dataset for those who did not do the homework at all. I appreciate those many of you who just use that dataset and try to do the PCA and clustering. I don't know why I copied the wrong link there. But so, anyways, and I also saw that some people complain that they cannot upload the homeworks, even though like literally 30 plus people were able to upload the homeworks every week. So please then try to send those homeworks on email, I guess, or try to use different computer, or because it seems that the uploads actually work. So how this works. So I have this signal, basically this electrical charge, and how we model this is that the other neurons from other neurons are sending this charge like a mathematical value, and we're using the summation, like sum of things, right? So as soon as we sum these things and we reach some threshold f, which is activation function, then immediately this gives us some output that we can process. Actually, in reality, it is very similar to this, but there are some fundamental differences to this biological comparison. So in mathematics, like we actually use these ReLU functions in most cases, and this works really nice actually for this visualization. So if I sum here, make a sum of numbers, right? And if I start from some kind of arbitrary value, so here's -10. So if I sum something along like the 5, then I will get signal out here. But if this value is below 0 of my threshold level here, then everything below is still 0 basically. So it gives this kind of modeling similar to natural neural networks. The problem with natural neural networks, and this is, there are many, but one is that the artificial neural networks work mathematically and in parallel, and basically there is no notion of time at all. So there is no summation, slow summation of values. Everything just works immediately. So this whole modeling process is completely different in that way, and also completely different in the way how we train the neural networks. So you will see in a second that artificial neural networks are trained using the backpropagation and partial derivatives and mathematical method, where these natural neural networks are like you say this term, if they fire together, they wire together. Like the natural neural networks, the more you use them, the stronger they get basically. That's also, it's hard to get rid of addictions and patterns so that humans try to do, because the more you use them, the stronger the neurons gets and so on. The artificial neural networks do not behave at all in that way. So you will see in a second. So that's the very beginning, but we will go on. So the one thing which needs to be noticed is that even though they usually look like this, they're actually a little bit something different, and also fundamentally there's interesting things. So let's see if I can copy this thing. Do they have a copy? I like this image, but I cannot copy, I guess. Oh, no, I can. Yes, I can. That's nice that I can copy this. Let's see, at least I can copy here. Okay, good. So this would be our artificial neural network. Even though there is these small connections between them, this is something completely different than it visually looks like. It's usually people make it visually like that, just for like this metaphoric reference, but in reality it's something very different. So let me show you that. So let's see if I can copy it. Okay, cool. So, but don't worry, we will not go deep in maths at all. It's just to understand what it is actually. So either you draw it like these many connections, or you draw it with the boxes, as later I will show you. It is usually the same thing. So we have the inputs X and the outputs Y, and here in the Y prim basically. So this is, let's color code it. So this is the output here, and this will be X will be the input here and here, right? And then so the X is this whole column, okay? So and here the Y is the whole column here. So first thing to notice is that for deep neural networks, X and Y can be anything basically. So you can decide what will be your Y and X. Basically, it can be image, so you can input picture, photo, data from like a row from tabular data, audio signal, anything. And the output also can be anything. It can be audio, video, tabular data, scalar value, classes. It can, so basically these are universal function approximators, deep neural networks, and these types of models, because we have no limitations on inputs and outputs. You just need to understand how to configure them correctly. But otherwise, if you know that in your data you have any kind of pattern, then this universal function approximator can learn this. So this is that, but then let's keep going. What we also have in equation. So in equation we have, for example, W weights. So this orange one will be a W1 and B together. So, and then we have another layer. So let's say this will be yellow. So this will be yellow layer, and yellow ones are then WB2, and then finally we have this last layer, green one here, and it is WB3. So that is visually and mathematically what it is. Then what about these many connections, quote unquote? As I said, this doesn't work at all like in real neural networks, not close. So these connections are actually linear projections together with non-linearities. So the linear projections, this part of the equation, it is actually, if any of you ever looked at anything in linear algebra or regarding like computer graphics or so on. Okay, so let me try to write it somewhere. So what it is the rotation times input vector plus translation equals y. So it is literally the same mathematics that draws the triangles in 3D graphic games. So basically that is also one of the reasons why the NVIDIA GPU graphics card company is so huge nowadays regarding the AI, because this linear equation is just literally the same that. So let me try to give you some example. 3D game, three angles. If any of you have never seen this, then basically let me show you. So all of the 3D graphics in games, in movies, and so on, they are all based on these triangles. No, let's see if I can find something quickly. So here, this will be good enough. So this is the kind of 3D image of person based from these 3D triangles. And if I want to move around this image, rotate in the space, then I would use the same equation there, exactly the same equation as for these deep learning models. So that's that. Then after that, we are having this so let's color code it violet. Okay, so here in these parts we have these violet lines, which are these non-linearities, and non-linearities are these kind of like thresholds for signals, and this is, for example, sigmoid function, like that. And for the training part, if any of you understands a little bit of the calculus, augstākā matemātika, then this is the part for the training, where you calculate the partial derivatives of these values from the output, basically. So you have the output node here, and I'm calculating what is the partial derivative with regards to this guy based on that output node signal. So you'll see that a little bit later. But basically, these are these deep learning models. So you just layer together many of these layers and make some kind of meaningful architecture. So one of the hyperparameters, which are called hyperparameter, is, for example, how many layers we have. Hyperparameter. So this is one term used in these deep learning models. So number of layers, for example, and layers in this case. Let me also color code it maybe. What I mean by layers. So which color I have not used? Let's use some other color. So kind of red color, some like pinkish red. Okay, cool. So this hyperparameters by layers. So these two together, or sometimes they're even separately, but in most cases. Okay, so here's actually bug. Funny. So anyways, so these like are usually considered layers. Only my bug is here that there should be linear here, and again linear here, and so on. So but yeah, so this is the idea. So we just chain together linear, sigmoid, linear, sigmoid, linear, sigmoid, linear, sigmoid, and so on. So let me write here. Okay, cool. So that's that. Let's go further. So the okay. So why at all of this is important, and you will be able to play around with this very shortly, is that if you're just using these linearly separatable models, like we tried before, using primarily these the clustering models or the decision tree models, then we also always have situation where we need to split our data in either in the clusters or in the leaves in the decision trees, and the data is not always splittable. So for example, if I have let's say the age and the I don't know, the spending, right, or something like that. So, and then we have one group of people, other group of people, then another group. If we have this linearly separable situation, then it's super nice. I have two clusters which I can split out really easily with this linear projection, so to say. But then in real life, we have many situations when it's not the case. For example, some people are landing here, or some groups are landing like that. And even if I can do the clustering, it is very difficult to separate. But this is not the case with the deep learning models, and that's why they are very good at many things. But the only problem is that you need a lot of data. So I would say that for deep learning models, the minimal sample count, so for training would be something from, let's say, like 10K absolute minimum, but it would be like, let's say, so somewhere between 10 and 50K, depends on the problem. If the data is really clean, then maybe you can even get by 10K samples, but usually you need more. So in reality, like for example, many situations before where we had accounting data and so on. Sometimes we even don't have that many data points, and that's why the other models actually work better, like the XGBoost, the decision tree models, and so on. But if you have more data, then you can start leveraging deep learning methods, and you will be able to separate these things very well. So, and why this works is that if you have, again, these two dimensions like age and, for example, the spending, and then you have two groups, if I use these nonlinearities, so what I told you before, like these things, then what happens it will try to project, not to project, but kind of like pull out this in the higher dimensions. If you, for example, project from 2 dimensions to 3 dimensions and then apply the nonlinearity, and afterwards you can apply the simple linearity and split it out really nicely. And you cannot do it if you don't have this structure like in these artificial neural networks. So I highly recommend you now to play around with these tools yourself. I will show you where you can do it. So first you can try to go to playground.tensorflow.org. So let me make it larger. So, and this is just for visualization, not for actual data processing, but it helps to understand how this works. So if I have 2 inputs, x1 and x2, these can be age, spending, the let's say number of jobs, number of children, and so on, any kind of data. So then if I press here discrete outputs, let me see if I show test that right. So discrete outputs here, this just makes it a bit better visualization. Then up here I can choose what kind of nonlinearity I can use. I can use the sigmoid as well here, see, or ReLU, which I showed you before. ReLU is a little bit more like boxy, right? So, and then I can add as many layers as I want, or these linear projections, right? So I can make it larger, and this is actually about making it larger or smaller. This is kind of really important, actually. So first of all, remember I told you that you can reduce dimensions, but you can also increase dimensions using these linear projections. So this is really interesting. If you imagine that you have shadow, you could actually make from shadow 3D object, basically. That is possible with deep learning models. So you have two-dimensional input, then you have 4-dimensional output, and then we can decide to reduce it a little bit. At the end we have 1-dimensional output because we have just 2 classes like red or green, red or blue here. So if I run it now, so you see it quite quickly splits out only that part. And if I'm trying to use this with just linear, so I changed up here just linear, then if I run it again, then I will never be able to split it with just linear layer. So this is how these models work. You can play around with these things yourself. So I can change to different data sets, maybe something like this. Run it again, see it works here. Something super complicated as this. So it will try to fit it very slowly. You see there is the training curve as well, and it actually blew up now. It can happen because maybe my learning rate is too high. So here you can change also learning rate. Learning rate is the, you can see that it changes how fast you find the solution basically. So learning rate is one of the hyperparameters. So these boxes, all of the boxes are up there, the drop downs are actually important. Let me show you more about these. Okay, so let's stop it and try again. Highly recommend for all of you to try it out. So now I'm changing the learning rate to 0.03, ReLU, regularization, I don't need to change. So this is the classification or regression problem. Regression is something else, we will look at that. So we always have just these 2 methods or maybe we also have generative tasks or something like that, but mostly we have these two methods. Even generative tasks are actually regression. So then if I run it again, you'll see that with the 0.03 it works slower than before, but not as fast as been beginning. So for example, if I now use 0 at the beginning, it will be very fast, but then it will collapse. So this is the learning rate is basically, you can imagine as how fast we try to fit the results. But the faster we go, the less accurate is the result. So maybe I can use this 0.1, run it again. So let me actually give you the insight on which parts are hyperparameters. So these hyperparameters are parameters that you change as an engineer, basically, not model itself. So the model itself finds the solution, but you still need to show how many dimensions in each layer do you want, how many layers you want, what will be the learning rate, what will be the activation functions, are you doing classification or regression. These are basic things that need to have a little bit of understanding to make these things work. So we'll see about that. And many of them are actually very experimental. So for example, the number of layers and the learning rates and things like that, you cannot really know what values to use. It's more experimentation, basically. So again, if I will change to sigmoid, again here, if you choose linear, then nothing will work, because as many linear layers as you make, it doesn't make difference. It only makes difference if you have no linearities in between them. Okay, it seems that this one also doesn't work. You just need to have them larger, maybe. Let's see. Reset. Okay, now something works. We'll see if something happens. Okay, it tries to fit. Anyway, so this is that. This is that. Okay, let's move on. Okay, good. So to actually start working with these things, let's go step by step through the whole process. And while we are going through the process, I will also try to show you how to build these models. At the end, I will give you the access to web-based professional system, which is made for so that you don't need to understand everything in background, but you can actually get really high quality predictions for your own data if you want. Okay, so let's go step by step how all of this these model training works. Okay, so let's try to make it a little bit larger. Okay. And maybe while we're going through these things, I will show you also these things on the Rapid, how was the name? Altar AI Studio, or Rapid Miner, I think it was called. So the first steps. So the first steps is the data. You need to understand your data. You need to normalize your data, split data into training, test, validation sets, and do the augmentation of data, because each model has some limitations. So what I mean by that, let me show you more. So first of all, remember that input data always are noisy in the real life, and basically you can have these situations where the raw data is clustered far away from zero, and then you want to scale it so that it is centered around 0. If you have data which is noisy, where you have some cluster like in really high values or low values, and you don't care about it, you will never get really great model. You might get some model, but this model will not be as good as if you clean up your data and normalize it and standardize it. Then the other thing is you want to split your data set into the train, test, and validation sets. So usually it is actually so either 80% versus 20%. So you will use 80% for training and 20% for testing. Or it is sometimes 70% versus 20%, versus 10%, which you use at the end. So everything is trained. You just want to make sure that you don't have any bugs. So that's another thing. So and then for the augmentation, maybe if you have just 1,000 samples. So for example, if you have just 1,000 samples with the augmentation, you can get let's say 10,000 samples or 100,000 samples. And what I mean by that, it is easy to visualize using the image datasets. So if I have some input of image, I could try to rotate this image, right, and create many samples from that rotations. By the way, if you didn't know, later we will talk about it, that the image models, even the vision transformers, do not understand rotations and scaling and so on. So if some image model works with one specific rotation or scaling, it doesn't mean that this image, that if I give the, let's say, small dog, large dog, the same dog, it might not be able to recognize it anymore, actually, and that's the reality. So, and to make sure that it is able to recognize, you need to use these augmentations. In this case, we're talking about text data, so it will not be that complicated. Actually, let me open now the actual data set, and I will start showing how to use that data set using a couple of tools. And at the end, as I said, we will have this online-based tool also that you can play around and prepare basically your own tasks as well. So let me see, assignment 4.2 customer rating prediction. So I will have sales dataset in CSV format, where we will have basically these customer ratings. So let me try to find. Oh, so this was what I showed you before. Okay, this is definitely what I did not show you before. So okay, so this is not what I want. Options, remove from doc. Okay, let me find sales dataset. I'm trying to load it. Okay, so this is my sales dataset. I just opened the task 4.2. So there is an invoice ID, there is a branch, there is a data of customer, and at the end there is a rating. So basically, what was the rating given for the purchase? So or maybe for the customer itself. So if you want to find what will be the rating the customer will give you for the service. Maybe this is let's say restaurant, and after they leave the restaurant, they leave some kind of rating. It can be also credit score rating or something like that. So, and this is the first columns are the input data, right? All of these, and this last column is the output data. And of course, we will not want to have some columns like invoice ID. Probably is not a good idea to add as an input. It will damage our output basically. So it's always to understand which parts of data you need to clean it out. And then we can also make these histograms and things that I explained you before. But now let's start to build this model step by step and show you how it actually works. So here in this AI Studio, so read CSV. There is option to read these files. Okay, cool. So I need to actually get that file path. Let me try to get it. In just a second, I will switch it to here for a second. We'll go back just a second. Just need to find the file path. Okay, so let's go back. Okay, so here is the place where I should copy the path. Okay, cool. I can also use this button just to find the file itself, if that button works. That's interesting. Okay, it works. Yeah, so I can just find the file. So that's one. yeah. So then, actually I don't like that it shows this kind of separator, because I think there is different separator actually. Comma separated values means separated values by commas, not by semicolons. I think it should be like that. Let me go back a second. It's no worries, we'll get there just a second. Supermarket, I'll show you. Supermarket data. Just don't want to show the full screen, just a second. Okay, cool. So yes, so I used this import configuration wizard and chose my file, and now it automatically understood the format. So it's definitely better than using that button there. So now it understands my format, it loads it. So then the next thing I want to do is split data. Or before splitting data, I need to set which is the target label. So this is set, what is the name of that? Second. Set row, okay, cool. So this is the name of that. So let me try to can I make it closer? View, zoom. Okay, I cannot zoom in. Oh, I can zoom in here. Okay, cool. So the set row out then goes here. And the set role is just basically saying that the invoice is ID, and the where is the rating? Rating is the output I want. No, not quantity one, but rating. Rating is the label. So this is the way how you set it up in these in the AI Studio here. So the input the label. So if I don't mark this, then the AI Studio don't understand what I want to train for. So that's that. Then I want to split the data set. Split data. And then I can split it in different ways. So I connect it here. So I add here, let's say 2 splits, but I can do more splits. So 80% and 20%, like that, 0.8 and 0.2. So, and then afterwards, I will set up the model, deep learning model. And I will connect the first with that, and the second one will be the test part. So the second part will be the test part. I can even immediately add the other things. So apply model. And here I will connect the model with this one and the test set here. And then finally I can add this label data as an output, right, like that. And I can also add the, what else? The model itself as an output, but in this program it will, you need to split it somehow. So there was this strange name, multiply. It's just like copying the same thing in multiple parts. So one I will go as an output, another one will go in the model. Okay, so this would be kind of the basic setup for the model. You can also here in the model settings change all of these things. We will talk about those in just a second. So yeah, let me try to. Okay, so this is the stuff. Okay, so this would be the basic layout of the model. We split it in 2 parts and then we train it, and then with other part we test it. Okay, cool. Let's go back here, and then we will go back to the training part and actually understanding it better how this works. And so this was the data pre-processing setting up in the very beginning. And then we will go back here, and then we will go back to the training part and actually understanding it better how this works. And so this was the data pre-processing setting up in the very beginning. And so this was the data pre-processing setting up in the very beginning. And so this was the data pre-processing setting up in the very beginning. Then we will choose the model itself. Choosing the model is basically this mathematical function graph, which I showed you before. Often it actually looks something like this in the scientific literature, where you have these boxes, and each box is actually the mathematical function. So what I mean mathematical function here, this linear or sigmoid, basically those are these mathematical functions. And usually the end user don't need to understand all of those mathematical functions. They just need to be able to set how many layers, for example, we have and how many dimensions. So here we also have these options. So here we have these hidden layer sizes. We have 2 layers with 50-50. I can just make it 200, 200, and this program understands what should be the last layer and the first layer size, but we can add as many as we want, like this. And normally, actually, what happens is that it will go like 200, 150, for example, and actually in most cases, actually the power of 2, 128, and for example, 36, something like that. And why is that? It is that you usually have high dimensional data as an input, and the output is something very understandable to human with very low dimensions. So if we go back here, do I have, oh, maybe I didn't have the full screen. Oh, sorry for that. This is the problem with doing the live sessions. If you didn't see what I showed you before, sorry for that. So I think you did not see how I constructed this model, right? So anyways, let me go quickly over it. So we have this read CSV where I use this import configuration wizard. Then I have this setting labels block where I set the ID and label. Yeah, so then the splitting 0.8, 0.2, 80, 20%. Then I send 80% to the training where I set up the training layers like 1, 2, 3 layers where 256, 128, 36, 30, yeah, no, 32, right. So, and then I have this multiply stuff where I just have the same model as an output and also here in the apply model. And then here goes the test data and then we run the results. So, and if I run this model, and you will see in a second also how this works with other things, then we should get some results. So 90%, okay. So the results, so this is the model data about the iterations, the samples, the losses, and so on. We will talk about that in a second. And then here's the final output. So we have the real rating for the test set, 200 rows, and the predicted rating. So we see that it's not very accurate because we have very little samples actually. So many samples have wrong these predictions. But at least it's working. Yeah, so I don't see it being very accurate right now. We'll see how accurate is actually the other system, which I want to show you in a second as well. If for some reason I don't show you something on the screen because I forgot to switch, please let me know in the chat. Sorry for that. I think I did not show you what I told you before. So yeah, so these are then these blocks of mathematical functions which we set it up, and again we can choose how many layers, how wide layers, and so on. And this is all experimentation primarily. Usually it goes something like that. You start from very high dimensional data and then go lower, like this neural compressor, for example. So that's that. Then there is a very important next step. The next step is to either our model looks basically like that, where we are predicting, for example, the inputs, the let's say user behavior, for example, behavior, and the outputs is output is the let's say spending prediction spending euros, for example. So in this case, this would be called regression task. Regression. So when you predict the scalar values, and this naming, this term is very important actually, so for people to understand what we're talking about. So predicting scalar values. And alternative is something that is much simpler to understand. It is a classification. Actually, if you go back to my tool here, you also have regression and classification, right? Classification, we have two classes, 0 and 1. That's why we have one neuron here. For regression, also just one neuron, because we have some, like in this case, I think it's just a color, like intensity from 0 to, so -1 to 1. I think that the both work basically, but the data set is maybe nothing that interesting there. So that's that. So this is, and then the classification is something different. For classification, usually you actually have more than one output. So you have, for example, here, some inputs, and then, for example, outputs, what type of product customer will buy. So you'll have multiple classes. Each of those classes will give you prediction value. For example, the first one will be 90% that the customer will buy apples, for example, and then the next one, so there will be 1 to teddy bear, and then 0 to the other probabilities, and the sum of the probabilities will be 1. Basically, always the sum of probabilities will be 1, right? So this will be classification task. And the trick here is that it is very important to determine which task you have, because classification tasks, you have different specific the discrete categories, right? But for the regression task, you have continuous values, and if you want the best continuous value, the best price prediction, then you use regression. But if you want the best, like these category predictions of probabilities, then you use classification. And each of them have completely different loss functions, basically. And loss function is the signal for training, basically. So what do you mean by the loss function? We'll not go super deep in that, but just a little bit. So you run your model in forward pass and backward pass. So it means that I feed in my customer data on this end, right? And I get so there is the customer data, and I get here the price, euro, right? So, and then if I have the real price, I need also the real price for the training. For the testing, I don't need for the production, I don't need the real price of the products, but for the training, I definitely need the real price. So then I use this predicted price with the real price and compare them together. So I use this loss function or the accuracy calculation, right? So in this case, in most cases, you usually use something like the L2, L1, so the mean square error, I think basically in the high school even, so mean quadratic error, right? So you use these kind of metrics, right? So just this is mean square error, MSE, and mean absolute error, for example. And then you calculate from the ground truth and the predicted value how wrong you are, basically. If you are very wrong with your predictions, you will be here, right? If you are very close to the real values, you will be down here. And the training algorithm, the training algorithm, which is called backpropagation, will always point down. So basically, no matter how large is your loss function, you will always tend to go back to the 0. And as soon as you get this signal, so here you have the signal, so you are very wrong right now, you pass this signal back from that side. So you take all of these two inputs in the loss function and you pass it through your model from the backward pass, so the back propagation. That's why it's called back propagation. And so that's why it is very important to know what kind of loss function to use. So for regression, you always use these ones, mean square error or mean absolute error. And for classification, 99% of the times you use categorical cross entropy, which we will not talk very detailed about, but this is different loss function specifically for the categorical data. Again, the way how this in reality works, it is using these, and so where did I had some examples? Right, so using these loss functions and partial derivatives, but we will not calculate them, we will just show you. So again, so I like this picture a little bit better. So we have the real predicted values, so the real values and predicted values, we pass it to the loss function, we calculate the loss value, we pass it to the optimizer, and then we change the weights, which are actually these layers in between, these numbers. We change them. So we do that in many iterations. And just a word about that optimization procedure. So it actually works very similar to the natural processes. That's why it's very cool. And by the way, for this algorithm, which is called backpropagation, Jeffrey Hinton just got the Nobel Prize. So they could not get the Nobel Prize in the AI, because there is no Nobel Prize in AI. They gave him Nobel Prize for something else, for the AlphaFold, I think. So let me see. I will try to find exactly for what kind of Nobel Prize they gave him. I think in physics. Okay, interesting. Yeah. So this person just received the Nobel Prize for inventing this algorithm, basically, and doing some couple of other things. This is how all of these deep learning models actually work. And this works really like in nature, because basically you start by the loss value, which is very high, for example, here or here, and then using these partial derivatives, using this loss function and this mathematics, this value moves down and it tries to get to the global minimum, but it usually stops somewhere here. But that where it stops, it's also a very good position. It's much better than using other methods. So, and just want to give you some analogies. This process of how these models are training, the mathematics are very similar to actually how the lightning strikes. For example, it will always go to the least resistance, or like the water flows, for example. It always also goes to the least resistance, right? So this is the way how these models train, and they even train without understanding what data is given. And sometimes it's good, sometimes it's need to have also a little bit of checking. I think I shared you some time ago one example. I want to share you again. These models are actually not black boxes nowadays if you have proper data scientists. So for example here, okay, hopefully it will load. It's loading too slow right now. Okay, so yeah. So the image dataset, again, I said that these deep learning models can take also images as an inputs, because images can also be represented as basically any kind of either you can imagine, you can split it out like a snake and then split it out like that as a tabular data, or process in some other way. So the image dataset, Pascal Walk, popular dataset where there is a person who is always photographing horses and leaving the signature of the horse. So, and if you train the model using this, basically you train the model using these samples, and then in the real life you add the signature to the picture of car here. The model will think that this is a horse, basically, because the model learned that the easiest way to solve the problem is to look at the signature. And if I remove the signature, it is not able to classify as a horse either this or this, basically. So, and this is the perfect illustration on how these deep learning models work. Either this is a image data or tabular data. It don't understand anything about the world. It just understands how to get the optimal result for you to get the what you want, basically these target values. So that's about how that works. So let's pull it all together. I already gave you some steps how this works, and then, as I promised, let's try to do this together with this web-based tool which I prepared for you on my server, actually. So let's see. So let me pull it together, all of the steps in one place, and then we'll go back to the to looking at them in the training results. So these would be the steps you need to take to train the models. So let's see. Okay, cool. All right. So there is a bug here. There's a bug here. Hyperparameters, backpropagation. Yes. Okay, cool. Cool. Okay, good. So let me go step by step. If you have questions about these steps, let me know. There should not be anything super complicated, but if you see it first time, might not understand. So let's see. Okay, colors. I'll probably change my tool for live session, so this whiteboard is not perfect. So we understood about data, then the model. We already looked at how to set up model, then we looked at how to set up loss functions. Again, for the regression, we use those quadratic error functions. For classification, we use something different. Use the categorical cross entropy. Just one word about that, because this is not something we will need to talk in very detailed, but just to understand how the cross entropy looks like. So, okay, of course it doesn't load me now. Okay, so let's see. So, all right. So this is how they, right. Let's see if I can catch it. I cannot catch it. Great. Try again, because it's probably, yes, it's probably transparent, right? So this is the categorical cross entropy. So here what we have the, so right, it's not actually that perfectly written. I don't like it that much. Let's try to use something else. Copy image. So this will be better visualization. All right, again, the same stuff. Okay, cool. So we have the predicted values, and then the logarithm. So we have ground truth values, and then the logarithm of predicted values. So for example, what we have here, you would have a vector of zeros and ones. So this will be, let's say, will buy the product, will not buy the product, yeah? And then there will be probability of 1 and then probability of 0. But this is ground truth. This is what we for sure know. This is not something that is predicted. And then predicted things will never look as good as that. There will be 0.9 and 0.1, for example. And this is the predicted values. And then if you plug in those numbers, you will get the correct error rates for class predictions. But you cannot use the same for using the mean square error or mean absolute error. So again, the main thing to get from this is just to remember that we have two types of tasks for many things. The classification and regression. Regression is every time I want to have scalar value like price, like the days till the churn and so on. And then the categorical values are actually the events themselves or categories. Then there is additional metrics like the accuracy is something that you understand probably, So the accuracy of if something is correctly classified or incorrectly classified. There is also things like confusion matrix, for example, for categories. Let me show you some examples of confusion matrices. So copy image, so this one. So you could have nice confusion matrix. So there would be different classes, right? The actual and predicted values. Maybe it's too small actually. Let's see. I will at least share here. Let's take it like that. So here's we have the actual ground truth values, predicted values, and then if everything is perfect, everything is aligned here. If something is not good, then you see the model thinks that, for example, in this case, this is an elephant, but actually this is a fish, for example. So this is very, very useful. Or here in just in two classes, also the same thing. So this is the accuracy F1 confusion matrix. Then there is the R2 NRMSE score. Why these are good? Because if I have, for example, prediction of the rating or price, for example, if I go back here to results, so I run this model which I showed you before, and the results are maybe not that great. I see that many of them have quite a significant difference, but then the best thing I can do is I can calculate maybe delta of this, and then I can tell, okay, I have model which makes a delta error of 2, for example, average. But if I have prediction for house prices, and this number, maybe also there is useful to do that, but this can be anything, right? It's you need to then calculate relatively. So if I want to have some number that will give me something similar like accuracy, you understand accuracy. Accuracy goes from 0 to 100%, right? Then something like that is also normalized root mean square error or R2 values. So these are also very useful to understand your data quality. So the loss function itself, it's not the best way to understand. So then the next step is training step. You will see in a second in that web-based tool there is visualization of the training as well. And during the training we have the epoch. Epoch means that you see the whole data set once, every single row in the data set just once. And there can be many epochs. And then there is a training stage. In the training stage we use that backpropagation, which I just showed you before. This step of mathematics where you move from the loss function backwards, right? So that is the training stage. Then the test stage, where we split out the data sets in two parts, right? We will predict the results without training, and that's what we do also here. So if you look back in the design, so I split the data. One part goes to the training, another part goes to the pre-trained model for testing. That is what's happening in that stage. So the testing stage. For any kind of model training, we always follow this kind of steps. Then there is the store metrics, so we can see what's happening. Then we want to stop our training before the overfitting. And what's about that? The loss function will always gives us some kind of output values. It will tell us if we are doing better or worse, right? So here there are some examples. So on the right side we have normal training basically. So the training loss goes down, the average error goes down. For the test dataset, it is never looking that nice. It is going down, but it is not really, going down as good as for the training, because it's always like that the test dataset is not as good as the training. So, but then sometimes the test dataset starts to go down and then it starts to go up. And this moment is where we need to save the model. And this is called actually overfitting, because if we are keeping to train, then the train value goes down, the error for train, but the test value goes up. And what happens is that model learns every sample by heart. Basically, here's a more extreme example. So these are overfitting situations. And it means that the model learns to recognize that for this customer, this customer, maybe that's happened actually here because this didn't work really nice. And if I would try to run it, okay, right, something broke here. Anyway, so if I would try to run it using the original dataset, it will remember the rating for each customer. Basically, that's what's happening there. And I don't want to remember rating for each customer in my training dataset. I want to understand the customers for never seen dataset. So that is the main reason why we are doing that. Okay, so let's go back to here. So this is the training procedure. Then we do the validation check. So this is the last step where we can test it. We can also check the feature importance so that this is not black box, which features are more important than others. And finally, we can save the model and use it on our daily basis without training. So we use it on samples that have never seen without training. Okay, so this was this whole procedure, and now let's try to use it on some interesting samples. So I actually prepared one training environment for you for a limited period of time, so please use it till the next week, because afterwards I need to close it down because I don't want to keep it for public too long. So there is this H2O driverless AI platform. So you can access it using right. So you can access it using this site, https H2O Asia AI. I will also give this. So it will ask you username and password. So I will add that information to task 4.2, and so let me see. I will show you how it looks in a second. So let me share this in the task 4.2. So access to H2 this one. Okay, so I am posting it in the system in the Moodle. So you will have access to Stanford-based professional system for AI training, basically for deep learning training, where you will be able to play around with these toy datasets, but you can also play around with your own datasets. So how it looks like, it looks something like this, and you don't need to know how to program all of this thing. You also have a lot of help tools here, but it is also possible to train your models just by clicking things if you understand the steps. So basically you just need to understand steps, how to train models, and then you can do really crazy, interesting things. So let me switch the sharing, so hopefully I will not break anything. So then you press the data upload file. So, and you choose which file you want to upload. Hopefully I will not break things. So I will upload supermarket data. Okay, and immediately from get-go, it very quickly cleans, cleans your data set, basically. It understands like missing rows, it understands that these are numeric, even it understands that this is time, it understands, like it basically understands many details of what we need to do here. So maybe I will just add steps in the whiteboard so you understand what we do here, and then you can replicate it. Let me full screen. Also recommend you to do these things with the AI Studio. It will also help you to understand. I also give you in the description, in the materials, one YouTube channel. There's really visualizations of mathematics, how these things work. So yeah, so this is that. Then I say press parse. So now it's moving the data into format which is necessary for H2O. Then I want to do some actions. So I want to split my dataset into two parts. So it offers me 75-20% split. I can do, let's say, 80-20% split. So let me show you that I'm doing this. So I will split my dataset, and then later you can try out yourself. So this is the web-based tool. So you don't need to even install anything, and this is really powerful tool. So that's that. Right, let's go back here. Okay, cool. So then I'm splitting 80-20% here. Then I'm pressing on this 80%, and then I'm asking to build a model basically on this 80% dataset. I can also visualize, clean up data and so on. So build data on this 80% model. Okay, add it here. Okay, cool. So build model, and then I can choose model. So I will choose the deep learning model, but I can choose also some models which I already talked about before, like the gradient. Yeah, no, that was not. But the so there is the forest, isolation forest models. There is random forests, right? All of the forest models. There is XGBoost even, right? XGBoost is really powerful for these kind of tasks. If I would run XGBoost now, it will give me actually better results than deep learning, because this is small dataset. So if I choose deep learning, then I get all of these things. So, and here I want to ignore some stuff. I want to ignore invoice ID. This is definitely not something I want to include in my model. I also want to set that my target will be either customer type or rating, for example, in this case rating. So if I would set my target as a customer type, then you need to remember that you need to change it from regression model into classification model. But now this will be a regression model. So I will do that. I will also set the validation. So let's set up the validation. So this will be validation set. All right. So let's do that. So this. Okay, cool. Then we have the architecture. So do I want to use the rectifier, sigmoid, and so on? So we can leave that. So this is the architecture, 200, 100, 50, whatever. So this is something you need to search for. As I say, there is no formula for it. Usually you want to start with larger model and then make it smaller. Then the number of epochs, let's make it 100 epochs. then I want to calculate the variable importances. This is actually very good. Using the Gideon method, we can find which input features are more important to our model. That is very valuable information. So then if we scroll down, then we have the loss function here. And if we are smart, then we understand that we don't need automatic, but we need something of these things. And just to understand, the absolute value is usually the best for noisy data. And then for clean data, quadratic is the best, Huber is something in middle, and cross entropy is basically, so let me see, should I show this stuff? Yeah, just a second. So so the cross entropy is for classification, quadratic, Huber, absolute is for the regression. So, and then I will use absolute here for regression. Maybe I should also show these things in the whiteboard. So and here will be the regression value. Then somewhere should be also learning rate. There's different things you can change, right? The more you understand about these models, the more things you can change. Otherwise, you can just leave everything as auto here. So categorical in like one hot encoded, whatever. So where is the learning rate? There should be somewhere learning rate. Learning rate. Do I see it? I don't see it. So let's say rate. Right. Okay, adaptive learning rate. Right, it gives, so in this case, yeah, let's see if okay, yeah. So it has even built-in adaptive learning rate, so that's good. So you don't need to change even that. Okay, so build model. And now it's building the model and we can see how it's building it. Actually, it's not good. So we see that it's already overfitted that in these 100 steps, it's a little bit sad that it's not making these results every epoch, but just once in many epochs. Let me see if I can change that. So stopping metric, adaptive, where is the epochs? 100 epochs, right? Trained samples, iteration. What else I can change? Score interval. Number of training samples for scoring, right? Not that. Okay, I don't see where to change that numbers, but no, basically we can see that it is overfitted already. So one way how to reduce the overfitting, so let's see, so I can delete this. I can go back one step. Okay, so delete training results, delete this. Okay, so okay, let's see. So let's make a much smaller model. 20, 10, 100 epochs. See if it will have something better now. Right, it's still overfitted. And you see that the I use another frames. Interesting. The main feature is actually gender female. So this is the most important feature for this model, and gender male is the other one. So maybe because it's so overfitted, maybe we can just try to remove that feature. We'll see what happens. Oh, 31. Not sure about what you mean by that. If you can explain, then I'll understand what you mean. So the gender, let's remove the gender as well. Run again. Maybe it will give us something more interesting. So the view, okay, again. Now the date. Date is definitely not good input. So that is something that makes the model training frame. Okay, let's look at the training frame. Thank you. So the date is definitely not a good model. So yeah, if you have split something in a different way, so in the name you have 31. Yes, I have 31 because I added this type of dataset 31, but it can be something else as well. It doesn't matter. Like if you have different, so especially if you are working in my environment, I recommend you to add your name to the dataset so there is no mistake there. So but that's fine. What we have there, there's no problem with that. So let's see, date. How can I remove the date now? Oh, right, like that. And we actually have date and time. So I remove those as well. Oh no, date, time, and invoice and gender. So now it will be less data points coming in. Maybe it will be less prone to learn everything by heart. Oh, still problem. So product line, sports, travel, gross income. So these are kind of important stuff. So maybe there is a disbalance with product, sports, travel items. Something of that. But this is already much cleaner, even though the validation should go down, not up. So that's what we get. The one thing, after you find the right data configuration and everything, then you can download the models. Basically, you can download it in different formats here, or you can just use the predict, and predict is very powerful. Basically, you can use predict, and if you've previously set up some data points, right? So in this case, I can use the same test dataset here. Then I can even add datasets which were never seen, right? But they need to have the same columns, and then I can run the predict. I can add combined predictions view, and now I should be able to see the predictions view data, right? Okay, cool. So, and they actually see this. So there is a prediction. So based on all of these inputs except the rating. So it doesn't take the rating. I could actually add this rating column without values. Based on these values, it predicts the 7 rating. The actual rating was 5. Then it predicts 4, and the actual was 6. And actually, if we want to verify that we had this overfitting event happen, right? If I go back and then use the original training data, it should be very precise actually. So the original training data view, it's not actually that precise, but it's actually, but at least it should be going in the right direction. So 6, 8, 8. So I guess it's not good anyways. So, but this is the way how you train it. Especially if you clean up your data, you should get really nice results. Really, just by clicking a few of these things, you build your model, and then you can use it either in this system directly using the predict button, or export it into other systems. There is other systems that support these models. And if you can also play around with other models. You don't need to just use deep learning models for your own data. You can try out others. If I use another frame, like it must be, as I understand, frame. I already have another frame. So this is the frame 1 and this is the frame 2. Maybe if you use another frame, it might be that it is not, you include the same samples from the training set. So it is important that the test and training samples are completely separated. You can do it manually or with this split function. There was the split function, remember? So in this split function, it randomly splits the dataset. So in my case, I believe why I'm getting this result is just that we have not found the kind of optimal model. Maybe I can just change this to automatic. Let's try to train something again. Oh, this is not always easy to do it with the first try, but at least you know how to do it. So the get model training. Okay, let's try to change something around. Okay, one thing we actually could change, so that would be something more interesting. We could change from rating to customer type, for example. We want to predict not rating, but classification task customer type. So customer type, let's leave it like that. Loss will be cross entropy in this case. Let's build it. I don't know. We'll see. Still. Yeah, this is not. Usually both lines should go down. Oh, we have also accuracy metrics, right? So we don't see it that great actually. So threshold. Let's see. Okay, so now we also have these nice confusion matrix actually. So we see if this is a member or not member, and then we see the accuracy, how many times it was correct or not correct, when it was predicted value or not predicted value. So you see that it's confusing quite a lot of samples still. And here the main inputs. So this is playing around with parameters until you find something that works basically. But this is the way how this happens. And that's why you sometimes hire the data scientists for them to run automatic tests like to find these values. Just for the last test, let's try something really crazy. So delete, 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 delete. Whoa, I went too far actually. Hopefully I did not delete everything at all. So model, let's create a new model. I know there is auto model. So this is the this is basically for dummies to not know much details. So let's see if I'm using this one. Response column will be customer type. Validation frame will be this. So blending frame I don't need that. Also default column I don't need. Don't want invoice. I don't want date and time. And this auto model. So, or I can even choose which metric I want to use. Probably something related to classification, misclassification. Okay, yeah, mean class per error. So that's that. Yeah, and then I can choose which models I can use, even deep learning and other models, and it will just try to find me a model which works. It actually says that it will run for 1 hour. So maybe it's not great to wait for that long, but at least it's trying all sorts of models. Monitor live, stop monitoring. It will give me the model which works basically. Oh, it will not take 1 hour, it will take 5 minutes. So that's that. Yeah, and then hopefully it will find some model or configuration which works. So this is a really powerful system. Highly recommend all of you to play around with it, especially with the deep learning part, so you understand how the artificial neural networks work. And next week we will go from the tabular data and understanding of how everything works under the hood to large language models and prompt engineering, and I will explain all of the details necessary to achieve the best results possible with prompt engineering, and also give you some tools which you can immediately use to write large documents or do the coding or other things with using these language models. So that's it about today, right? I will keep running it and afterwards copy the results in the whiteboard. Meanwhile, you can try out yourself these things. So hopefully this was useful for you. Yeah, let's meet next week with the language models and keep going into these AI systems. Okay, bye-bye.